The Reeb graph of a scalar function represents the evolution of the topology of its level sets. There are very few generic algorithms for computing Reeb graphs, even though there are optimal algorithms for computing contour trees. In this video, we illustrate an easy to implement near-optimal output-sensitive algorithm for computing the Reeb graph of scalar functions defined over manifolds or non-manifolds in any dimension. Consider a solid torus. To ease the illustration, all solid models in this video are rendered transparent. Define the function value at every point in the torus to be the height of that point above the floor. A level set consists of all points where the function attains a given value called the ISO value. Notice that as we increase the ISO value, the topology of the level sets change. Let us now track these level sets. A new level set component is created at a minimum. It now splits into two components at a saddle. Upon reaching the second saddle, the two components merge into one component, which is finally destroyed at a maximum. These 4 points where the topology of the level sets change are known as critical points. The Reeb graph shown on the right expresses this evolution of level sets as a graph. Nodes of the Reeb graph correspond to critical points of the function. Let us now consider a more complex model with the height function defined on it. Notice that each arc of the Reeb graph can be mapped to a cylinder in the input. Each cylinder is a collection of level set components that are topologically equivalent to each other. The level sets at the two critical points defining the arc form the boundary of the corresponding cylinder. The key idea in our algorithm is to use this mapping to obtain the arcs of the Reeb graph. Our algorithm takes a triangulated mesh as input. The function is sampled at vertices and linearly interpolated within each simplex. The algorithm first locates and classifies the critical points of the input. Consider a vertex in the mesh along with its neighborhood. The link of that vertex consists of the mesh induced by its adjacent vertices. The upper link is a mesh induced by adjacent vertices having a higher function value, while the lower link is a mesh induced by adjacent vertices having a lower function value. A minimum has an empty lower link, while its upper link has one component. An index 2 saddle has one component in its lower link and two components in its upper link. An index 1 saddle has two components in its lower link and one component in its upper link. The lower link of a maximum has one component while its upper link is empty. For a regular point, both lower and upper links consist of one component. We use this characterization to locate all critical points. All degeneracies are handled using simulation of simplicity. Next, we sort the critical points in increasing order of function value. The algorithm next computes the level set for each critical value called the critical level set. Specifically, we compute only those critical level sets that form the upper boundary of each cylinder. We march through adjacent triangles starting from a triangle incident on the critical point. If a saddle has two lower link components, the corresponding critical level set has two components. The final step of the algorithm computes the arcs of the Reeb graph by tracing through each cylinder. Starting from a triangle incident on the upper link of the smallest critical point, we march to an adjacent triangle having vertices with a higher function value. We continue marching until we reach a triangle that contains the level set at an ISO value equal to the function value of the next non-minimum critical point. If the destination triangle belongs to a critical level set, we insert an arc between the corresponding nodes in the Reeb graph. We repeat this process for all critical points in the sorted list. If the upper link of the source critical point has two components, we launch two traversals from that critical point, one for each component. Upon reaching the function value of a higher critical point, if we find that the destination triangle does not belong to its critical level set, we continue our traversal until we reach a higher critical level set. When all critical points are processed, we are done computing the Reeb graph of the input function. Tracking the connected components of the level set requires only a one skeleton representation, which can be extracted from the triangles of the input mesh. In case of non-manifolds, we relax the definition of critical points to include all vertices that modify the topology of the level set. So the algorithm works directly on the two skeleton representation of higher dimensional manifolds and non-manifolds. Our algorithm has a running time of the order of n plus l plus t log t, where n is the number of triangles in the input mesh, t is the number of critical points, and l is the size of all critical level sets. We have noticed that L is usually order of n in practice, so the running time in practice is close to the optimal bound of O of n plus t log t. As a byproduct of our algorithm, if we trace a path through the triangles traversed, we get an embedded layout for the Reeb graph. This embedding is guaranteed to lie in the interior of the input domain. A breadth-first search traversal within a cylinder, instead of traversing a single path, marches through all triangles that belong to that cylinder. We then specify different transfer functions for each cylinder, thereby creating a volume rendered image that distinctly highlights the user-specified areas of the volume. For example, consider the silicium dataset. The Reeb graph of the height function is embedded within the volume. Two atoms are now highlighted by assigning a different transfer function for the cylinders corresponding to a loop in its Reeb graph. The Reeb graph computed by our algorithm also finds applications in interactive surface segmentation, skeleton extraction, and topology repair of models.